Hey YouTube, welcome back to my data structures and Typescript series. In this video we're going to go over binomial heaps. So this is the story so far. These are our runtimes for the binary heap. We have enqueuing and dequeuing being logarithmic because we have the swim or sink elements throughout the height of the tree. Peeking and checking to see if our heap contains a specific element is constant. And increasing and decreasing a key are logarithmic as well because of the sinking and swimming that's necessary in those methods. Another method that's quite important is merge, and for regular binary heaps, the runtime for that is O of n plus m, where n is the length of, let's say, your first heap, and m is the length of your second heap. The need for merging priority queues are quite important, and one example of where merging priority queues are used in is this minimum spanning tree algorithm with this name. I'm not gonna try pronouncing that because I'm gonna botch it. But in the minimum spanning tree algorithm, where we find a spanning tree for a specific graph, the merging operation for priority queues is very important. Here's a diagram to get a better picture of what it looks like when we merge two heaps or priority queues. And these pictures are from a professor from Stanford called Keith, and I'll have his lecture slides in the description below. So we have a priority queue on the left and a priority queue on the right, and the bolded element is the smallest element. So obviously these priority queues are minimum priority queues. When we merge them, we get them into one cloud, I guess you can say, and now we have two minimums, and then we update the minimum to be the smallest of the two. So now the new minimum of the entire newly merged priority queue is 6. So the problem with regular binary heaps is that merging takes O of n plus m. We construct a new heap with the heapify technique. If you remember from the previous videos, we used the heapify technique to construct a new heap in a linear amount of time. So there's n plus m nodes in total. We put that in an array, and then we heapify by syncing the nodes starting from the second row onwards. So this is okay, we can merge with regular binary heaps, but it's linear, and ideally we want something faster like logarithmic. So the solution to this is something called binomial heaps, and that's what we're focusing on today. A binomial heap is a data structure that implements the mergeable heap abstract data type. And the binomial heap implements merge in O of log n plus log m time. So this is faster than just your regular n plus m. What is a binomial heap? That's a great question. Let me answer that for you. So a binomial heap is a forest of binomial trees. Each of these are a binomial tree. So let's figure out what a binomial tree is before we learn about what an actual binomial heap is. Binomial trees are recursive in nature, and they have degrees associated with them. So trees with larger degrees are built from trees with smaller degrees. A binomial tree of degree 0 is a single node. So we have this single lone node, 13, and it has a degree of 0. If we merge two binomial trees of degree 0, then we get a binomial tree of degree 1. So here are two binomial trees of degree 0, 10 and 4. Just kind of ignore these pointers, these edges right now, because I just kind of cut them off a picture. And then we merge the two by making one of the nodes the parent and one of the nodes the child. So let's make 10 a child of 4. And that's a binomial tree of degree 1. If we merge two binomial trees of degree 1, then we get, as you guessed it, a binomial tree of degree 2. Here we have two binomial trees of degree 1. Ignore these black edges going outside of the picture for now. And we have 1, 9, degree 1, 7, 15. So 7 is one root and 1 is another root. And let's make 7, let's make 1 the parent, and let's put 7 as a child of 1. So we merge them, we make 7 the child of 1, and this is a binomial tree of degree 2. Here we have two binomial trees of degree 2, and let's merge them by making 3 one of the childs of 2. And let's merge them by making 3 one of the children of 2. So we make 3 a child of 2, and then now this is a binomial tree of degree 3. In general, we have the base case definition, which a binomial tree of degree 0, which is denoted by B0, is just one single node. And then the definition for any binomial tree of degree k is just two binomial trees of degree k minus 1 linked to each other, where one of them is now the new parent and one of them is going to be one of the new children of the parent. Another way you can look at the definition of a binomial tree of degree k is that its children are binomial trees of descending order. So we have k minus 1, k minus 2, all the way down to 0. Here's a bigger and clearer diagram of binomial trees. We have the base case definition where a binomial tree of degree 0 is just a single node 13. And then a binomial tree of degree k is created by linking two binomial trees of degree k minus 1, where one of the trees becomes a child of the new root. So let's say for degree 2, we have two binomial trees in degree 1, 7, 15, 1, 9, and 7 now becomes a child of 1. And then here, order 3, we have this binomial tree on the right-hand side is degree 2, and the red is degree 2, and we make 3 a child of 2. And this is now a binomial tree of degree 3. And without concrete numbers, this is just a general diagram of the shape. We have the shapes of binomial trees from degree 0 to 4. Here, 4, you can see these are two binomial trees of degree 3 in the actual structure if you break it down. And this is now a child of this root here. And this entire tree is now a tree of degree 4. So a binomial tree has a few properties. A binomial tree with degree k has exactly k children. So you can see here 0, 1, 2, 3. A binomial tree of degree k has k children. 1 child, 2 children, and 3 children. And a tree with degree k has exactly 2 to the k elements or nodes and height k. So here height is 0, height is 0, 1, 0, 1, 2, 0, 1, 2, 3. And you can count that each tree has 2 to the k nodes. So we have 1, 2, 4, and 8, and then 4 would have 16. The next property is that the children of the root are binomial trees of themselves of degree k minus 1, k minus 2, all the way down to 0. I don't know why I put exponents there, just ignore that. So here, a binomial tree of degree 3, we have the root, and then the children are binomial trees of themselves. So here we have a binomial tree of degree 2. And then this one's a degree 1, and this is degree 0. You can tell by the color highlighting. And the last property that we have is that a binomial tree of order k has k choose d nodes at depth d, hence the name binomial tree. So if you're familiar with the binomial coefficient, at any depth d, there's going to be k choose d nodes. So going back to the definition of a binomial heap, a binomial heap is simply a forest or list of binomial trees. And binomial heaps have two properties. Each binomial tree obeys the minimum heap property, so every node has to be less than or equal to all of its children. And if a binomial heap is a max binomial heap, then it's going to be the maximum heap property. So either or, minimum or maximum. And the second property that binomial heaps must satisfy is that there can be maximum one binomial tree for a specific degree k, so 0 or 1. Here are two examples of binomial heaps, and notice that these two properties are satisfied for both of these heaps. So here in this binomial heap, each tree obeys the minimum heap priority. You can check for every node that it's less than all of its children. 2 is less than all of these children, 3 is less than all of these children, and so on. So it's similar to your regular old heaps. And this satisfies the second property as well, is because there can be either 0 or 1 binomial trees for degree k. So here we have one tree of degree 0 and one tree of degree 3. There's not 2 trees of degree 3 or 2 trees of degree 0. This is a binomial heap as well because each tree obeys the minimum heap priority. So this is a minimum binomial heap. You can also have max binomial heaps. So for this example, we're just doing minimum. And it also satisfies the second property where for any degree k, at most we have one binomial tree of degree k. So here we have a tree of degree 0, 1, and 2. We don't have any overlapping trees. Here are two more examples of binomial trees. You can notice that both of them satisfy the minimum heap property. One thing that you'll notice though is that the ordering of the roots of the trees, so you can think of this as a forest and these are individual trees. That's what I like to picture in my head as a nice mental model. There's no inherent ordering of the values of here. We have 18, 3, 6, so we go from a higher number to a lower number to a higher number. Here we go from a higher number to a lower number to a lower number. There's no inherent ordering in the value of the roots. As long as for each tree in the binomial heap, for each binomial tree, All we care about is that it satisfies the minimum or maximum heap property. So both of these satisfy that, and both of these satisfy the second property, where there can only be 0 or 1 binomial trees for a specific degree k. So here we have degrees 0, 1, 2, and here 0, 1, 3. So there's never any two binomial trees of the same degree k. So here's the real intuition behind binomial heaps and why they are efficient. A binomial heap has at most one binomial tree with degree k. We know that because that's the property that we've created for binomial heaps. So here's the intuition of why we're using binomial heaps, and this will tie into how the merge operation is conducted with binomial heaps. Remember from our second property, that a binomial heap has at most one binomial tree with degree k. So here is an example of a binomial heap, and we have at most one binomial tree for any degree k. So we have a tree to degree 1, degree 3, and degree 4. Now, remember that since all binomial trees have 2 to the k nodes, that was one property that we've noticed of binomial trees, this means the largest tree has degree log n. This is the number of times we raise 2 to get n. So here we have a binomial tree degree 1 and degree 3 and degree 4. So hence there's going to be 2 to the 1 nodes, which is 2. There's going to be 2 to the 3 nodes, which is 8. And there's going to be 2 to the 4 nodes in here, which is 16. The property that these trees have 2 to the k nodes combined with us limiting the number of binomial trees to at most 1 for any degree k means that we're just counting in binary. Here's the binary representation of the number of nodes in this entire heap. And you'll notice that we have 0 here because there's no binomial trees of degree 0. We have 1 because there's 1 of degree 1. We have 0 here because there's no trees of degree 2, and then 1 here for degree 3, and 1 here for degree 4. And this is just counting binary because we want to count 1 for 2 to the 1. So we have 1, 2, 4, 8, 16. That's binary, and these are the same number of nodes in these trees. So we can represent our binomial heap with binary numbers, with 0, 1 representing the existence of a binomial tree at degree k. And this isometry between binary numbers and binomial heaps allows us to merge binomial heaps very efficiently. So now let's talk about the merge operation. That's the operation that we kind of highlighted before, that we wanted to get down from O of n plus m to O of log n plus m. And here we're going to call it union. So we're unioning two binomial heaps. We have one binomial heap here and another one down here. The first step in performing a union of two binomial heaps is performing a merge sort on the two heaps with respect to the degrees of the binomial trees. So going back to the previous slide, we have the first heap, h1, as a binomial tree. It has a binomial tree of degree 0, 1, and 2. The second binomial heap has a binomial tree of degree 0, 1, and 4. So when we merge them, we're going to sort the new, we're gonna merge them together, and then we're gonna sort them in increasing order of degree k. So here we have the 2 trees of degree 0, then 2 trees of degree 1, and then 2, and then 4. So now we have our newly created heap, which is formed by the merge of the previous two heaps. But now we are violating one of our binomial heap properties, the fact that we can only have one binomial tree of degree k. So here we have 2 of degree 0, we have 2 trees of degree 1. This is okay, 2 is okay, and degree 4 is okay. But we need to fix these, and the way we're going to fix them is link them together. So the way to get rid of these two trees of degree 1 is to link them together and form a tree of degree 2. This takes O of log n plus log m time because we have to traverse the entire forest and link the trees. So remember that in here there was log n trees from the first heap and log m trees for the second heap, and now that we have to traverse the entire forest, the entire list of trees, to link them and make sure that we don't have two binomial trees of the same degree k. So now let's perform the first link. We're going to go from left to right and traverse this forest. We see we have the first two nodes, 12 and 18, with the same degree 0. So let's link them together and create a binomial tree of degree 2. But one thing that I didn't mention before when just going over binomial trees, is that this new tree has to satisfy one of the other properties of the binomial heap, and that's the minimum or maximum heap invariant. So we have to check which root. In this case, this is a minimum binomial heap. We're going to check which root is the smallest of the two. So we see that 12 is smaller than 18, so we're going to make 18 the child of 12, not the other way around. So notice here that we moved 18 under 12, and now we have a binomial tree of degree 1. So in the union algorithm, we see that we have the next 3 trees of degree 1. We're going to leave this alone, and we're going to link these 2 trees of degree 1. Again, we check which root is the smaller one, so then when we do link them, we maintain that minimum/maximum heap invariant, and in this case, it's a minimum binomial heap, so we're going to check for the minimum one. We see that it's 3, so we're going to put 7 under 3. We do that, and now we have a binomial tree of degree 2. But now, of course, we're violating the invariance again, because now we have 2 binomial trees of degree 2. This one right here and this one right here. So let's link them, and of course with the link, this is going to be repeat and rinse now. We check which root is the smallest, 3. So that's going to be the root of the newly linked tree, and we're going to put 15 under 3. So here we put 15 under 3, right here, and now we have a new binomial tree of degree 3. And now the binomial invariant is satisfied because we have at most 1 binomial tree for any degree k. So looking at the runtime for the union operation, it's log n plus log m, where m is the length of the first heap and m is the length of the second heap. If we look at the pseudocode, we see that the first step is merging the 2 heaps. These heaps are already sorted according to the degree, so all we have to do is something similar to the merge step in merge sort. So this is just going to be a linear amount of time, which is just the lengths of the 2 heaps, which is log n plus log m. But it's great now that we have all of the trees consolidated under one sort of data structure, a heap. But now this merged heap variable is potentially pointing to a heap that's violating the second invariant, which is a binomial heap can have at most 1 binomial tree for a specific degree k. So we're going to consolidate that, and that's just like binary addition. We're adding these bits, which represent trees, and this is going to be log n plus log m time. We're going to be traversing the list of roots and consolidating it by linking these roots together. Linking is just constant because we're just moving pointers, so the main work is just traversing this entire list of roots. So now let's talk about inserting into a binomial heap. Inserting into a binomial heap, not tree, this is a typo, is simply taking the union of the existing heap and a new heap with the new element. Because we take the union, insertion is just log n. It's like log n plus log m, but m here is just 1 heap with 1 element, so that's log of 1, which just is 0, and that's a constant. So the dominating term of the expression is log n. So here we're going to enqueue2. So we're going to pretend this is a brand new heap with just 1 element, and then we're going to take the union of the existing heap, which is the blue nodes, and the new heap, which is the yellow node. So in the union step, we pretend that we've already performed the merge, and now we're in the consolidation phase, and we see that there's 2 trees with degree 0, which violates our binomial invariant. So like the union, we're just going to do what the union does and link them together, where the new parent is the smaller node to maintain the heap invariant. So we're going to make 2 the new root, and we link it together. So now we have a tree of degree 1 and a tree of degree 2. So this is the binomial heap that was unioned, and this is the result after we enqueue 2. Now let's enqueue 1. So we create a new heap with a single loner element, just 1, and now we take the union of this heap and this heap of blue nodes. When we take the union, we perform the merge, so now this is under 1 heap data structure, and when we consolidate, none of our trees are violating the invariant, where we can't have 2 trees of the same degree k. We have a tree of degree 0, 1, and 2. So we're all good. Now let's enqueue 6. So this is a single heap with an element of 1, 6, and then we have the existing heap, which is all the blue nodes. Now let's perform the union of these 2 heaps. So the first step in the union is to merge them together into a new heap sorted by the degree k. So now we have 2 trees of So we merge them together and we see that we have two trees at degree 0, which violates our invariance. So we're going to link them together. We link them together where one's the new root because one's smaller than 6. But now we see that we have two trees of degree 1, so we have to link them together as well. We link them together, we make 2 the child of 1 because 2 is greater than 1, and we have to maintain our heap invariant, and yeah. But now, again, it repeats, and we see that we have two trees of degree 2, which violates the invariant, so we have to link them together. And we're going to make 3 the child of 1 because 1 is less than 3. So we do that, we put 3 under 1, and now we're finished with the union because everything is consolidated. So insertion, the runtime of insertion is logarithmic, log of n, and you can think of binary addition. All we're doing is adding 1 to another binary number. So in the worst case, we have to carry bits for all log n digits. The next method we're going to cover is the delete min method. So with regular binary heaps, we had constant access to the minimum. It's the root. But now we have a forest. We have a list of trees. So we don't know which element is the smallest. We don't know which root is the smallest. Here is a heap with 2 trees, but there could be a heap with 4 trees, and we have to essentially find the smallest root, which takes log n time because we have to walk through the forest, and the length of the forest is log n. We could store a pointer to the smallest root, but then we would have to, when we extract it and delete it, we're going to have to calculate that min pointer again and then potentially walk through the entire forest, which takes log n time. We'll see in the next data structure, which is the lazy binomial heap, how we can bring the runtime of this down to O of 1. So anyways, we're going to find the smallest root. In this case, there's only 2 trees. So, we walk through, we see one's the smallest element. So one's the smallest element for now. Then we see 9 is not smaller than the smallest element, which is 1. And then we get to the end of the list, and then we know 1 is the smallest root. So now we're going to remove it from the entire forest. We remove the smallest element 1 and save it for later so we can return it to the client. And now we have a fragmented tree. These children are fragmented. You can think of it as cutting the top of the tree. And we now have to fix this entire heap because we have these just free-floating children going around. The way we fix this is by taking the union of these children and the existing heap. So with these fragmented children, we're going to create a new heap out of them. And the reason we can create a binomial heap out of these children is because the children of any binomial tree are binomial trees themselves, and they're going to satisfy the minimum heap invariant as well. So we make a heap out of the fragmented children, and then we're going to take the union of the children heap with the existing heap, and here in this example it's just 9. So the first step of the union is to merge the 2 heaps together, sorted by increasing order of degree. So let's do that. So here we have the merge, we have the trees at degree 0, and then 1, and then 2. We see that after the merge, we're going to do the consolidation step of the union and ensure that for any degree k, we have at most 1 binomial tree with the same degree. So performing the consolidation, we see that we have 2 trees of degree 0, so we're going to link them together, and 2 is going to become the new root because it's less than 9, and this is a min binomial heap. We now see that we have 2 trees of degree 1, so we link them together. 2 is going to be the new root because it's 2 less than 3. 2 is less than 3, and we link them together to form a tree degree 2. We now see that we have 2 trees of degree 2. We'll link them together, make 5 the child of 2 because 2 is less than 5, and this is the new tree created with degree 3, and our heap is just 1 tree for now. So this is the final state of the tree, and this is the result of deleting 1. We delete 1, remove the node, like kind of cut it off, pretend like you're taking scissors and cutting it off from the tree, and then we're going to take the union of the existing heap with the new heap of the fragmented children, and this is the result. So now looking at the runtime for delete min, it is logarithmic. We first remove the smallest root, and we cut the root off from its tree, and this takes log n time to find that smallest root in the forest. We then create a new binomial heap with the fragmented children, and then we create a new heap by performing the union of this. So here is just like this heap, this dot union will union this entire heap, which is a class, with the children, and that takes log n time too. So this is just log n, and then the entire runtime is log n as well. And the next operation we're going to cover is the find min operation. This returns the smallest node in the entire heap. But now our heap consists of a forest of trees. We don't just have one tree, so we can't just look at one tree and that one single root. We have to potentially traverse the list and find the smallest root out of all of the trees in our entire heap forest. But one thing we can do is store a pointer to the smallest root and then return this root in constant time. So here find min, we'll just store a pointer to 3 and then return that. When we extract the minimum node from the forest, we can find the min again in log n time, and since dq is log n, that does not change the runtime of the entire operation of dq. Looking at the next method, we have decrease key, and decrease key does not change from the existing implementation of binary heaps. We just decrease the priority slash value of a node and swim it up in log n time until the heap invariant is satisfied again. So this is one tree in a heap. So let's say the client wanted to decrease the priority of this node from 20 to 7. So we're going to change that to 7, decrease it, and then swim it up until it satisfies the heap invariant. So we swim, and then it's good. The implementation for decrease key does not change, even though we have multiple trees now in our heap. It's just the same old as binary heaps, and if it needs to swim all the way up, it will, and it'll become the new smallest node for the specific tree that it is in. And of course, this takes log n time. And in the worst case, we're swimming up the tree with the highest height of the entire heap, so the height would be log n. The last thing I'm going to talk about in this video is how we represent these binomial heaps, these trees. And binomial trees are usually implemented with something called left child right sibling representation. So in the left child right sibling representation, we represent a multi-way tree where each node has 2 pointers, its leftmost child and its rightmost sibling. So here is a multi-way tree, and you can think of the canonical way that you might think of it, where each node has an array of children. So in the left picture, we have A has an array of children. It'll be B, C, D, E, F. Then B has 1 child, which is G, D has 3 children, which is H, I, J, and F has 2 children, K and L. So each node knows about all of its children. In the right picture, we have the left child right sibling representation, where any node only knows about its right sibling and its left child. So A knows about its left child, which is B, and then B will know its right sibling. So B will know C, C will know D, D will have a pointer to E, and E will have a pointer to F. So in one sentence, you can think of it as, instead of storing an array of children, you're storing a linked list of children. It's still possible for a parent to find its kth child. All we have to do is descend into the left child and then traverse right k times. So we're just switching basically from arrays to linked list representations of children. The left child right sibling representation is more space efficient than a traditional multi-way tree, but comes at the cost that looking at a node's children by index becomes slower. So this is just basically the pros and cons of arrays versus linked lists. So therefore, the left child right sibling representation is preferable if 1, memory efficiency is a concern, and/or random access of a node's children is not required. So here's a picture from the CLRS textbook, Introduction to Algorithms, of a left child right sibling representation for binomial heap. And this is the internal structure for the heap above right here. So we have a heap 10, 1, 6. One thing that's different from just left child right siblings is that each node has a reference to its parent, just so we can swim up, because we need to know the parent to potentially swim up the tree. So here we have a linked list of the roots, a forest basically. So here's 10, here's 1, and then here's the 6. And each root has a reference to the left child, and the left child starts the linked list of children. So going back to the use cases of left child right sibling representation, the first case might arise if you need to store a huge multi-way tree in main memory. And the second case, which applies to us with heaps, is that it arises in specialized data structures where the tree structure is being used in very specific ways. So the main reason why case 2 applies to heaps is because there's 2 common operations that we use with binomial heaps. The first operation is that we remove the root of a tree and process each of its children. So remember that when we're extracting the minimum from an entire heap, an entire forest of trees, we are cutting off the roots. So all we have to do with the left child right sibling representation is just delete pointers. The second operation that's common to binomial heaps is joining or linking two trees together by making one tree a child of another. So it's very easy to do this because all we have to do is just move pointers. We don't have to deal with arrays or anything like that. We're just going to be moving pointers. So to see what I mean, let's look at some ASCII diagrams. The first common operation was removing, and removing the smallest node from a forest of trees means cutting a root off. So let's say we have the picture on the left right here, and we know that this is the smallest root in the entire heap, in the entire forest. All we have to do is just cut off this pointer. We don't have to move any arrays or anything like that. The second common operation that we talked about in the previous slide was joining two trees together. Joining two trees together, of course, is found in the union operation, and to be exact, the consolidation step, the second step of the union operation, which is the consolidation step. So here we have two binomial trees, R1, R2, and you can think of these as just children 1, children 2, and it's very simple. All we have to do is, let's say we know that R1 is the smallest out of the two roots, and this is a minimum binomial heap, so we're just going to make R1 the new root of the new tree. We're going to make R2 the child, and then R2 is not going to change its children, but its right sibling is going to point to the children 1, the root 1 children. So we don't have to, move when we're linking trees, we don't have to move stuff in arrays or move it to the front of the arrays. All we have to do is just move pointers, which is very easy. So the cons of left child right sibling representation are that basic operations like searching, insertion, deletion take longer because we don't have the ability to index into specific children of a root. So that was an overview of binomial heaps, both the internal structure and the operations. If you were to remember one thing from this video, is to remember the important invariant that we have with the binomial heaps. One, of course, is the regular invariant, where every node has to be less than all of its children. That's just a regular heap invariant. But the second invariant that's very important for binomial heaps is to make sure that we don't have more than one binomial tree for a certain degree k. This gives us is the isometry between binomial heaps and binary numbers, because at most we only have one binomial tree of a certain degree k, and for each binomial tree of degree k there's 2 to the k nodes, so we're counting binary. When we have this, we get merge to be logarithmic because we're just performing binary addition. So that's why every time we mutate the structure, which is enqueuing or dequeuing, we make sure to consolidate and coalesce the structure such that our heap invariants are satisfied. Going to the runtimes, enqueuing and dequeuing are logarithmic because we're leveraging union/merge. Peaking is constant. The runtime for increase and decrease key do not change. In the worst case, we're sinking/swimming nodes up tallest tree of the entire heap, so that could be log n. And then of course unioning is just like binary addition, so it's logarithmic. The next data structure we're going to cover is lazy binomial heaps, which serve as a foundation as well for Fibonacci heaps. And lazy binomial heaps and Fibonacci heaps are all about being lazy. So we can actually get enqueuing and dequeuing to be a constant amount of time. So I hope you enjoyed, and I'll see you in the next one where we'll go over the implementation for these binomial heaps. See you then.